This is Chapter 17, Section 2, talking about capacitance. And we've got a few definitions here. A capacitor is a device that's used to store electric potential energy. So if you do build up this potential energy that's considered electrical potential energy, can you actually store it? And the term capacitance is the ability of a conductor to store this energy in the form of electrically separated charges. And we'll eventually get to a video to show you how capacitors work. The unit that we're going to use for capacitance is called the farad, and we use a capital F for it, and a farad is equal to a coulomb per volt. Getting to another equation that we're going to use, capacitance is the capital C. The Q here, notice instead of a lowercase q, they're using an uppercase Q, and this is talking about the magnitude of a charge on each plate, and you will get to see the plates that we're talking about when we get to the video, divided by the potential difference, which is delta V. So add this equation for capacitance to your set of equations.
Each of the metal plates is connected to one terminal of a battery. When the circuit is closed, charges are removed from one plate and accumulate on the other, leaving each plate with a small net charge. The transfer of charge stops when the potential difference between the plates is equal to the potential difference between the terminals of the battery. When the switch is opened, the potential difference between the plates remains. Because the separated charges on the plates have gained energy, the two plates have stored electrical energy. Capacitance is the ability of a conductor to store electrical energy by separating charges.
So again, going back and looking at this, notice that the charges do eventually stop. It says once the charge on each plate gets close to the terminal electrical potential energy coming off of the battery, then the flow is going to stop. So you can see you have mostly positive on one side, mostly negative on the other. So capacitance, it does depend on the size and shape of your capacitor. I mean, how much charge can it actually hold? If we look at another equation, it says capacitance for a parallel plate capacitor in a vacuum. It gives you C for capacitance, that lowercase e, naught, that stands for permittivity of the vacuum itself. That is a constant that it gives you there at the bottom. That's another Greek letter called epsilon. So that's your permittivity. You've got the area of one of the plates, and again, area is length times width, and then you have the distance between the two plates, and area is going to be in meters squared, distance is going to be in meters. So again, when you do meters squared divided by meters, you'll end up with meter there, which will end up canceling out with the meter that's in the denominator of your permittivity constant. And again, so this is permittivity of a vacuum. You do not need to memorize this constant. If you need to use it, then it'll be given to you. You just have to know what to do with it at that point. Permittivity itself, if you look up a definition for permittivity, it would say it's a characteristic which describes how it affects any electric field set up in it. So you can see it written there now. Again, it's a characteristic. Permittivity is a characteristic which describes how it affects any electric field that is set up in it. So permittivity of a vacuum, how is your electric field going to travel within a vacuum versus how would your electric field travel within air or within water or some other type of medium. The materials that's between a capacitor's plates can change its capacitance. Again, what's that material? Is it air or is it some other type of medium? And the effect of the dielectric is to reduce the strength of the electric field in a capacitor. So your dielectric that is there, that's going to be between your two capacitor plates, it is trying to reduce the strength of the electric field in a capacitor. You know, think about computers. Sometimes a little charge goes a long way. You don't want to fry everything that's around it. And that is the example they give you there is a button on a keyboard. You've got the key itself. You have a movable plate and a fixed plate that the key sits on top of, and then there's some type of dielectric material in between it. So when you push that button, you're going to change that gap a little bit. There is a material there that allows the electric field, and so electricity can actually pass through it, but again, you don't want too much.
Two parallel metal plates that are close together as shown here. The capacitor.
Sorry about that. We'll start over.
The simplest capacitor consists of two parallel metal plates that are close together as shown here. The capacitor is shown discharged with no net negative or positive charge on either plate. Connecting the capacitor to a battery causes the plates to become charged with an excess of electrons on the negative plate and an equal excess of positively charged ions on the positive plate. Here the plates are separated by an air gap, but most capacitors use a dielectric material or a vacuum between the plates. Regardless of which insulator separates the plates, the capacitance of a parallel plate capacitor is directly proportional to the area of one of the plates and inversely proportional to the separation of the plates. The permittivity of the medium is a proportionality constant, as shown here for the case of a vacuum separating the plates.
So again, pay attention to inverse relations, direct relations, how this is set up. It's nothing that you haven't seen before. It's just used in a different context. So another equation is given to you here. Again, we're dealing with electric potential energy. This time, instead of using some of the symbols and variables we used in the last section, we're throwing in the capital Q here. So your potential energy stored in a charged capacitor does depend on the charge and potential difference between the capacitor's two plates. So they've set it up as 1/2 Q, which is the charge, and then delta V is your potential difference. So add this equation to your list and we'll look at their sample problem. It says a capacitor connected to a 12-volt battery holds 36 microcoulombs of charge on each plate. What is the capacitance of the capacitor? How much electric potential energy is stored in the capacitor? So capacitance, that's your capital C. How much electric potential energy? That is PE electric. And this should be pretty straightforward as the PowerPoint goes through it. There's your given information. You got to change microcoulombs to coulombs, and then you are using the voltage on the battery. There's your equation for capacitance. Plug in the information that's given. So they do give you the answer in farads and microfarads. And then potential energy electric, it gives you the equation that was given. They plug in their data and they solve for electric potential energy, which is 2.2 times 10 to the negative 4 joules as an answer. So again, those are supposed to be pretty straightforward, nothing special about those. And your homework shouldn't be really too much more than that. Just as a wrap up, the equations that we've looked at, you had capacitance is Q over delta V. That was at the very beginning. You've had capacitance is your permittivity constant times area over distance. And then electric potential energy, we've looked at it as 1/2 Q delta V. And if you combine this with this first equation that's up here, do a little bit of rearranging because we're going to replace Q, then it ends up being 1/2 C delta V squared. So again, just trying to use a couple different equations, derive a new one. So that last one is one that wasn't produced within the PowerPoint.